Welcome to our series on business analytics, where we explore the practical use of spreadsheets in solving business decision-making problems. In today's session, we want to demonstrate the use of Microsoft Excel as a spreadsheet in solving linear programming problems. We use the graphical approach, which assumes two variables in a linear program. The process we want to adopt is first, to clarify the meaning and types of business analytics. We then follow this up with an illustration of a linear programming problem and how to formulate such problems algebraically. Thirdly, we demonstrate how the algebraic formulation of linear programming can be translated into a spreadsheet. Lastly, we apply the graphical approach in the solution to an LP problem. Through this tutorial, we want to emphasize that you can use the tools that you already have in your computer to carry out business analytics. We zero in on Microsoft Excel as an example of a spreadsheet model that is widely available and can be used for solving some of the problems that fall under the banner of business analytics. We have divided the presentation in two parts. The first part presents a few slides on the background of the linear programming approach using the graphical method. These are a few slides that give this background. And then the second part of the demonstration presents the spreadsheet solution using Microsoft Excel. Let us start by first looking at what business analytics is. A common definition that you find is that business analytics is a scientific process of transforming data into insight for making better decisions. So business analytics really is focused on how to make decisions better. Now, if you look at that definition, especially when you look at the meaning of the scientific process, especially when you look at this, when you look at the definition of business analytics, let us clarify this definition of business analytics. And a common conception of what it means is that business analytics integrates the use of computers, the use of statistics, and mathematics to solve business problems. So actually the scientific process attempts to identify the disciplines that contribute to business analytics. There are many disciplines, but the key ones are disciplines from the computational sciences. So we talk about computers, statistics, and mathematics. Now, when we talk about the use of computers in this scientific process, let us remember that computers make a particular process much more efficient and effective. Recall that efficiency relates to how well resources are used in each activity. Therefore, when you talk about the use of computers in business analytics, they provide us with massive processing power and speed to solve very complex problems. Therefore, business analytics leverages on advanced computational capabilities provided by computers to help in decision making. We also see the idea of effectiveness coming in by using computers, right? Effectiveness relates to how well the goals or objectives of an activity are being achieved. And if the goal of business analytics or BA is in effective decision making, then the integration of computers in this process makes the realization of objectives much better, much faster. The other discipline that you see coming into business analytics is statistics. Now, from a statistical standpoint, the insights provided through business analytics rely on data, and the discipline of statistics provides the language or the science that explain the manner of collecting, analyzing, presenting and interpreting data. Therefore, from a business analytics perspective, we recognize its quantitative approach to decision making. That's why the statistical discipline also comes in and has a lot of contribution in the techniques of business analytics. Lastly, the other key discipline is mathematics. And when you consider mathematics, mathematics simply provides us with the logic to express the nature of relationships of the variables that you find in the decision-making situation. Right? Mathematics is the science of structure, of order, and relation. And it has also evolved from counting, measuring, and describing shapes of objects. So, as a scientific process, the techniques also use the logic of mathematics to understand what is the nature of the relationship between the variables that are being considered within a particular business decision-making situation. But therefore, as we look at the meaning of business analytics, let's relate the scientific process to how specific scientific disciplines have contributed to the definition of what business analytics is, and what emerges is therefore a process that is considered to be scientific or quantitative in nature, relying on data to be able to provide insight to making better decisions in organizations. But the other thing is, what are the key categories of business analytics? And you find that the key broad categories are three, and we find what are called a group of techniques called prescriptive analytics. All right, and the focus of prescription or prescriptive analytics is to aid the decision maker or help the decision maker in deciding what should we do. Right, so it's more prescription. You are recommending what should be done. And under this banner, you find a number of techniques, business analytics techniques. For instance, when you talk about linear programming, one of the techniques that we'll start with to demonstrate the idea of prescriptive analytics. We talk about linear programming, we talk about network programming, we talk about integer programming, goal programming, the critical path method, economic order quantity, and nonlinear programming. These are just exemplars of some of the types of prescriptive analytics. Now, the way to know the difference between the three different categories of business analytics, that is prescriptive, predictive, and descriptive, is to consider the model characteristics. There are two considerations here. The first one is for the modeler to ask whether they know the nature of the relationship between the variables of the decision situation. So we talk about the functional form of the relationship of the variables. For instance, a common business situation is the calculation of profitability. And profits are calculated by deducting costs from revenues, or profits is equal to revenue minus cost. Just by expressing it that way, we are actually expressing a functional relationship between the three variables of that particular issue, profit. So we have profit as one of the variables, revenue is another variable, and costs is another variable. So there are three variables in that particular situation. When you're looking at model characteristics, the modeler must ask themselves, do I know the nature of the relationship? And the example I've just given, we know the nature of the relationship because you are determining profit by deducting revenue from cost. The second consideration when you're determining the type of business analytics is whether you have the values or you know the values of the independent variables in that decision situation. The example I've given, for instance, profitability is the dependent variable. Revenue and costs are the things that influence profitability. Before you carry out an analytics task, ask yourself, do you have the values of the independent variables? And in our case, that is profitability, that is revenues and costs. So if the values of the independent variables are known with certainty, then you can apply a prescriptive analytics techniques which will enable you to prescribe what should be done. And when you have this, then these are the group of techniques that you can apply on that problem situation. Now, to understand what predictive analytics is, the focus of the question is what could happen. And the model characteristics considered are you may not know the nature of the functional relationship. You do not know how the variables behave, right? However, you know or are certain about what the independent variable values are. So, unlike the prescriptive situation where you know both, for you to apply predictive analytics, you are focused on knowledge of independent variable values, but you may not know the nature of the relationship. This is where you find a number of techniques being applied. For instance, regression analysis, time series analysis, discriminant analysis, neural networks, logistics regression, affinity analysis, cluster analysis, etc. So a lot of the statistical techniques that you find are actually under this predictive analytics category, as well as machine learning techniques. While a lot of operations research and management science techniques are found under prescriptive analytics. And by the way, the concept of business analytics, is very strongly aligned to, disciplines such as operations research or management science or decision sciences. The name has changed over time, but the current name that is popular is what we're now calling business analytics. So we find a lot of statistical techniques are here, as well as machine learning techniques. But we also find what we call the third category of business analytics called descriptive analytics. And this asks the question, what happened? And descriptive and predictive both rely on historical data. Now, the model characteristic of descriptive analytics is that you should know the functional form of the relationship. This is now flipped from predictive analytics, right? In predictive analytics, you do not know the nature of the functional form. In predictive analytics, you know the functional form, but you do not have these values. So the independent variable values are either unknown or uncertain. And that's why you find the common techniques that you find here are either simulating a situation so that you're able to establish the functional form, or you using, for instance, queuing theory or queuing models. The PERT are mostly used in project management, as well as some forms of inventory analysis, inventory management, because you may also find inventory methods here under prescriptive analytics. But there are also situations where, especially when you do not know the independent variable values, where you can apply inventory models, and they are classified under descriptive analytics as well. So it depends on these the two considerations that determine where each of these techniques fall. So throughout these presentations, we look at each of the different types of business analytics techniques under the broad categories. And in today's session, we'll be focusing on linear programming, and specifically looking at the graphical method in solving linear programming problems. In the next slide, we therefore move to illustrate one of the, we start the process of looking at the linear programming problem. A common example of a linear programming problem is what is called the product mix. problem, or the production mix problem. So we therefore start the application of business analytic techniques by considering a product mix or a production mix problem that we can then use, then apply linear programming as one of the prescriptive techniques in solving this product mix problem. Now, to explain the production problem, let us remember that one of the key concerns of a company or a business entity is to determine the product mix. In other words, what quantities of each product should we produce? Typically, you'll find a company has more than one product. There are companies with one product, but most companies have more than one product. And therefore, they are focused on determining what is the quantities of products that they should produce. Right? The product mix is therefore the combination of products and or services that the company should produce or provide with the goal typically of maximizing their profits. So obviously the company produces products to maximize profit or sometimes to minimize costs. For example, in this example, if you read through the illustration, we are told that the company wants to maximize their profit. You're given details about the profits of $350 per each product that they are producing, and we are told they are producing two products, the Aquaspa and the Hydrolax. They sell the Aquaspa at a unit profit of $350 and the Hydrolax at a unit profit of $300. Now, for them to produce this profit, we are also told that there are certain constraints. You know that constraints must be there in organizations or in normal decision-making situations because we are faced with limited resources. For example, a company does not have all or cannot afford all the employees that they want. Therefore, they have limited budgets or they have limited materials, etc. So the goal of profit maximization is limited by certain constraints, and these are provided as part of the problem. Right, so let's remember that each of these products, therefore, or services usually requires different quantities of raw materials or labor or equipment and other resources that the products may need. So those constraints are provided. The varying quantities are considered as the independent variables that influence the goal, i.e. to maximize profit. For instance, in our situation, the company needs to determine what are the quantities of the first product, Aquaspa, and the quantities of the second product, Hydrolax, that they can produce in order to maximize profit. They don't know these quantities. These are the variables, the independent variables that they need to determine in order to maximize their profits. Therefore, each of the products or services will also generate varying amounts of profit, and therefore profitability, as I had indicated earlier, is the dependent variable. Now, the decision maker involved in determining the optimal product or service mix must decide on the quantity of each product or service that can realize maximum profit or satisfy demand at the lowest costs. In our case, in this particular illustration, we want to maximize our profit. This is given in the last question there. That the question is, how many Aquaspas and Hydrolaxes should Howie produce if he wants to maximize his profits during the next production cycle? In the next slide, we go through the process of how to formulate this problem as an LP formulation or a linear programming formulation problem algebraically first, and then translate this into a spreadsheet. This next slide summarizes the same A linear programming products mix problem into a mathematical formulation, into an algebraic formulation. We have captured the same information but mathematical, because we need to remember, for any business analytics technique to be applied, your problem must be translated into mathematical form. If we are applying a linear programming technique, then you need to change the problem into a linear programming formulation. And this is the format that it normally takes. The process of translating the problem into a mathematical form is what is referred to as analytics framing or analytic framing. So you translate the problem, which was described to you by the stakeholder, into this form, and it is this form that is understood by the techniques, the computer techniques that we are going to use throughout, right? In any linear programming formulation, to formulate it properly, you first need to understand the characteristics of those type of problems. And linear programming problems fall under a group of problems, a group of models called optimization models. And in optimization models, your intention is either to maximize a particular value. For instance, in this case, they want to maximize profits, or they want to minimize a particular value, which could be, in a company situation, they typically want to minimize the costs, for instance, costs of operations. So you need to understand the characteristics of optimization models, and the three key considerations are to understand what are the decision variables for your problem, what is the objective function, what is your objective, and what are the constraints that will influence that particular objective function. So we talk about three elements that are characteristic of the nature of LP problems: decision variables, constraints, and the objective function. Therefore, to formulate LP problems, you first need to understand these characteristics. For example, in the previous data regarding the problem that we want to investigate, we know that the objective is to maximize profit, and we were told that each unit of the first product, aqua spa, let us give it a label X. So X represent aqua spa and Y represent the second product, which is the hydrolax. You can use whatever labeling symbols that are convenient for you, right? This could be X1, this could be X2, this could be W and Z, your choice, right? But we have selected to use X and Y. Recall, we want to use the graphical approach, so we are adopting X and Y so that we know that the Y axis will represent these products and the X axis will represent the aqua spa. So the objective function is denoted in this format: 350, where 350 is a unit profit for manufacturing a unit of aqua spa, and $300 unit profit for manufacturing a unit of Y. And we were further told that during the process of manufacturing this, these are the constraints that the company will face. We were told that the company is faced with a constraint of they only have 200 pumps available. In the problem description, we were told that each product, each hot tub that they manufacture requires 1 pump each. So the total number of products manufactured should not use more than these 200 pumps, right? So the maximum number of pumps available as a resource constraint is 200, and we are told that each product requires a unit each. This is the expression given here, or the equation given here: 1x plus 1y should be less than or equal to 200. Now, the this side is called the left-hand side of the constraint. All right, and the left-hand side of the constraint contains the coefficients of, let me just repeat that. The data for the model consists of the coefficients in the objective function we have there, and the various coefficients in the left-hand side. So for the constraints that are shown here, these are the left-hand side values, which captures the constraint, capturing the unit. For example, in this first equation, 1x simply shows that for each unit of x that is produced, require 1 pump, and then it should not exceed 200. That is the same explanation adopted for these other constraints, right? We have the labor constraint, and we are told the company has a maximum of 1,566 hours, and that each product of the aqueous power product requires 9 hours, while each product of the hydrolux product requires 6 hours each, and that the total, the summation of all the hours used in producing the products should not go above 1,500, 600 labor hours. Right? So again, this is the capacity constraint in terms of labor, and this is the right-hand side value, while the coefficients will form the coefficient and the decision variables will form the left-hand side values of the labor constraint. And it is the same with the tubing constraint, where we are told that 12 feet of tubing is required for the manufacture of 1 unit of X, while 16 feet of tubing is required for the manufacture of 1 unit of Y, and that we should not use a total of 2,880 feet of tubing. So these are the 3 constraints that affect the goal, which is profitability. Now, in addition to these explicit constraints, we also need to remember that in any linear programming formulation, we need to take into account what are known as the non-negativity constraints. The non-negativity constraints simply imply that we cannot produce less than 0 units of products. It doesn't make sense, it's nonsensical. You should either you're not making any products, that's why we say the X and the Y should be at least equal to 0 or greater than 0. So you may find that the company has not made any product and made maybe some quantities of Y and vice versa. So non-negatively simply recognizes that you cannot make negative products. In the next lecture, we now see how to translate this LP formulation into a spreadsheet formulation. We now want to translate the algebraic formulation of the problem into a spreadsheet formulation. So the translation process simply implies that you need to ask the question, how can you represent this information into a spreadsheet? Remember that the information presented in a spreadsheet should be understood by the spreadsheet. So the way it appears as an algebraic formulation may be different from the way it appears as a spreadsheet formulation, as you can see in this example. So in the next few slides, we'll now switch over from PowerPoint to Microsoft Excel to show how to start representing an algebraic formulation in this format into this format, and how to solve such a representation in a spreadsheet format. So really the goal in this translation process is to organize your data so that their purpose and meaning are as clear as possible. So from this to this, and you want to present the data presented here in such a manner that it communicates to your stakeholders appropriately, right? Therefore, to this end, you should first spend time organizing the data for the problem in your mind's eye, right? visualizing how the data can be laid out logically before you start typing values in the spreadsheet. So think about this formulation. How would you want to, if you're presenting that information to an accountant, for instance, how would you want to present this information in a spreadsheet in a format that is understood by the stakeholder? Remember, the focus is on the person who you're going to present to. That is your stakeholder. Whether it is a chief executive officer or a marketing director or the vice president of production, who is the stakeholder and what kind of information would they want to see, especially when you present it in a spreadsheet format. That's why we say that the purpose of the translation process is so that uh, you are able to present your purpose and meaning to the stakeholder so that it's clear as possible. All right. Now, to achieve the result of a logical presentation of the information in a spreadsheet, um, every modeler should consider a few key goals. Right. You want to translate this information into a spreadsheet format. What goals should you focus on in terms of designing this? And a number of goals, these are design goals, have been provided. The first one is what we call communication. That the focus of communication really is visual appeal in a representation. How can you represent this information in a spreadsheet which your stakeholders can like, right? So the focus there really on when you talk about communication as a goal is how to communicate the relevant aspects of the problem at hand in as clear and as an intuitively a manner as possible. For example, if you look at this representation, obviously we have we have named our worksheet. This is a company that we are referring to. And recall that we were focused on maximizing profit and we represented it by using X and Y, all right? And those are our product values there. So we have highlighted the range where we want the units of X and the units of Y to be represented. And we have also captured the coefficients of the profit function just below it. So we know that for you to determine total profits, you must multiply uh, that coefficient value of profit with that unit that you're going to calculate there, plus that coefficient of profit 300 times that unit to determine your profitability value. So they are connected somehow, and you're able to provide the total value there. This value is very close to the source of the row and column totals. Right? So communication, therefore, uh, you are talking about enhancing the visual appeal. For example, the use of colors, where you place your different elements of what you are determining. Like you've seen, we are representing the coefficients of the constraint using different colors, as well as the totals of the left-hand side of the coefficients are represented using different colors as opposed to the right-hand side values. So we'll go through this process of translation, but we are emphasizing that communication focuses on improving the visual appeal of your spreadsheet presentation. The second goal focuses on reliability, and reliability communicates the idea that accuracy inspires confidence. For instance, we will need to put in a formula here to calculate total profit. And in total profit, we'll be multiplying 350 times that cell and 300 times that cell to get total profit. Now, you want that the formula that is here is accurately calculating what the actual profit is. Otherwise, we have spreadsheets that have very many formulas, and you want all those formulas to calculate the right amount. So if the model is not reliable, is not giving you accurate figures, for instance, then it does not inspire confidence. from your stakeholders. So when you talk about reliability, the goal of reliability emphasizes the accuracy of the model as a representation of the situation being investigated. And reliability has an obvious impact on the degree of confidence a manager places in the results of the modeling effort. The third goal of spreadsheet design is auditability. And we emphasize in auditability that logical layout enhances auditability. When we talk about auditability, we recognize that models that are set up in an intuitively appealing logical layout tend to be most auditable. In other words, can somebody else follow the procedure that you adopted in that spreadsheet model to arrive at similar conclusions? They may not exactly be the same, but do they, anybody else who goes through the process, do they tend to arrive at the similar sentiments, similar results that you have portrayed in your spreadsheet model, right? So uh, auditability has a connotation or has an implication to do with replicability. How replicable is your model? And when your model is replicated, uh, does that person end up with similar results? Then the other key goal is that of modifiability. And here, under modifiability, we recognize that, in any decision situation represented, for example, in this situation, the algebraic, the linear programming problem, there are likely to be changes. For instance, a situation may arise where the price of the first product now goes up. It's no longer constant at 350. Maybe it is now 400. All right. In designing, in having a spreadsheet model, you must take into account that the decision-making situation can change. It may affect the decision objective function, or there may be situations that affect the constraints. For instance, we may now have 400 pumps available. When that happens, what effort is required to change the model? That is the question. So modifiability implies that you can there should be minimal changes to the model in case the decision situation changes. So when we talk about modifiability, we recognize that the data and assumptions upon which we build spreadsheet models can change frequently. Therefore, a well-designed spreadsheet should be easy to change or enhance in order to meet dynamic user requirements. Let us remember that designing a spreadsheet model is not just a science, but it's also an art. There are various ways of, there's more than one way to organize the data for a problem on a spreadsheet. But you should keep in mind, you know, those goals of spreadsheet design so that you come up with a spreadsheet model that is acceptable or that is valid in the eyes of your stakeholder. The other slide will now show how to solve. So you will need to get into spreadsheet design, come up with a design such as this, which helps you to organize your data, right? So for example, we have now transferred the coefficient values into a spreadsheet model, uh, starting with the objective function, right? We have captured the coefficients related to the objective function under that cell for unit profits and that second cell, and we have also set aside cells for calculating the unit quantities of each of the products for Aquaspar at that cell and for Hydrolaxes at that cell. Directly below, and there's a logical relation. Remember that when you're determining the constraints are linked to the decision variables. The decision variable cells are up there. We have aligned them so that as we determine the pump constraint, we have captured the coefficients similar to how we capture the profit coefficients. we have captured the constant coefficient immediately under the decision variables, right? So that there's a logic in terms of the relationship between the different cells that you find in this spreadsheet. Therefore, as you design the spreadsheet formulation, you need to remember to organize the data, then build the model around the data. So we have transferred the coefficient values into a spreadsheet model of this format, and we'll see a practical application. And there should be some logic in how they are related. So organize the data, then build the model around the data. The second key thing we need to consider in the design is that we should not embed numeric constants in formulas. For example, when we are determining total profit here, we will see that we don't use the actual values, rather we use the cell reference for where this value is. So that is what we mean when we talk about not to embed numeric constant, but rather when you're inputting functions and formulas, you rather use cell references. So where $300 is, use the cell reference for that location in the formula. We'll do a similar case when we are inputting formulas for calculating the left-hand side values. The left-hand side values determine what the actual resources used. Remember, the right-hand side values give you what is available. The first constraint tells us 200 pumps are available. It does not mean that the optimal solution will use all the 200 pumps. That's not what happens in reality. So this column of the left-hand side values will determine what is the actual resources of each of these constraints that are used, even though we have a capacity constraint given the right-hand side. And therefore, this calculation is necessary because we are told what is used can be less than or equal to the actual capacity constraints. All right, so we will see how to input formulas here. We are not going to embed numeric constants in formulas in that place and in that place. And, as I've indicated, things which are logically related, e.g. the left-hand side and the right-hand side, values and constants should be arranged in close proximity to each other so that when you want to determine that value, you know that you are referring to that cell as you multiply with the unit, and then you're referring to that cell as you multiply with that unit to determine what is actually there. Right? So things which are logically related should be arranged in close proximity to one another. And as I've indicated, a design that results in formulas that can be copied is actually better than one that does not. So given that you're going to input formulas in each of these cells, once you have set up a formula here, can you copy it? Copying is better because sometimes you have a spreadsheet that is very big. Here we're only talking about 3 constraints that are captured here. In some situations, there are thousands of constraints. Think about a situation where you are manufacturing an aeroplane. An aeroplane has thousands, probably hundreds of thousands of constraints in the manufacture of a single unit of an aeroplane. So if you have constraint, if you are inputting a formula which can be copied, it is therefore better because we know that to take care of modifiability when there are changes in requirements, you don't want to change hundreds of thousands of rows, but rather maybe one point and then copy. In the next slide, we are going to show a sample of the approach, a sample of the steps required for determining the graphical approach practically. Remember that we want to solve this problem graphically. So just to remind you, our intention is to use the graphical approach of linear programming. And I want to emphasize that the graphical approach assumes that there are only 2 variables. In our case, the variables are to determine the quantities of aqua spar, that's the first variable, and determine the quantities of hydrolysis. Those are the two products. Those are the two variables that we want to determine. And once we determine those units, we are able to determine what is the optimal profit and what kind of resources are we able to use based on this profit that we have calculated. So in determining the graphical solution to an LP problem, the first thing that you need to do is to draw a graph like this, which we'll do, showing the constraint lines, right? So, and for you to draw these constraint lines, here is the LP formulation. So where we translated the algebraic formulation into a spreadsheet model. To draw these constraint lines, the information you need are the constraints information, right? And remember, if you have a graph, if you are to draw any line, remember we're talking about linear programming, and for linear programming lines, there must be flat lines or there must be straight lines, right? So they cannot be curved lines. And for you to draw a straight line, you need two coordinate points, right? So to determine the coordinate points, you actually need to make some assumptions. And in this block here, we have shown how to calculate the coordinates that are used for drawing these lines. So this you determine first before you draw the graph. Now, take the first constraint, for instance. We were told that the first constraint is 1x plus 1y should be less than or equal to 200. And this can be equated to be an equality, right? 1x plus 1y is equal to 200 because it is meant to be a line. It's showing a boundary. Therefore, that is the assumption when you're drawing the line. But as we look at other techniques, we'll see why that is done. So if you are given such an expression or such an equation, to determine two coordinate points, you must first make an assumption. What if x was 0? This is the point here. When x is 0 and you substitute the value of 0 there, what is y? When x is 0, then you can see that y will be 200 minus 0, which is equal to 200. So the first point, when you say x is 0, y is 200. And then to determine the second coordinate to complete or to draw the line is now you assume, what if y is 0? When y is 0, that is what is substituted here. X will now be equal to 200 minus 0, which is equal to 200. So when y is 0 here, x will be equal to 200. Here when x is 0, y is 200. So you need to determine these coordinates. We need to do the same for the labor constraint and the same for the tubing constraint. This is what the block does. And we have transferred these calculations to these cells here because for us to draw this, we need to pick these values directly from Microsoft Excel, from actual cells. So for the first constraint, the pump constraint, we have now determined that when x is 0, y is 200. That's the first one. And when x is 200, y is 0. We've done the same for the labor constraint, and we've done the same for the tubing constraint. So that, in our next slide, we then use these values to draw this graph. And after this, that's the first step for determining the graphical solution, draw the constraint lines. Then the next stage is to determine what is the feasible region of the lines that you have drawn. And that we will demonstrate and show that it should look something like this. So in determining the feasible region, part of it is to shade or identify or isolate where that feasible region is, and then determine what are the corner points, because the graphical approach requires that you know what the corner points are as determined by the constant lines. Remember that the corner points are delimited by the constant lines. Where they intersect, determine those particular corner points, and where they intersect also includes the non-negativity constraints. Remember that if we say non-negativity constraint should be more than or greater than 0, then that condition refers to the boundary of the axis. So that is the y-axis and that is the 0 line. That is the x-axis, that is the 0 line. So our reference is to everything above the 0 line. So we have drawn the constraints which delimit a particular section which is determined as the feasible region. Then we determine the corner points of the feasible region. And then after that, we calculate what is the profit in each of these feasible regions. And the maximum of those become our optimal solution. Now, to determine the profit of each of these feasible region, extreme points, we need to determine what the coordinates are for these extreme points. Now, in this block, this is where we determine what the coordinates are for each of these extreme points or corner points. To determine the coordinates of these corner points, there are two approaches that we illustrate in this demonstration. The first one is simply to look or eyeball to check, the coordinates of A is 0 and 0. So we see here point A. The approach to determining the coordinates is eyeballing, and we can see that A is at x is equal to 0 and y is equal to 0. In other words, if those are the coordinates of point A, then we are saying x is 0 and y is 0. And if you substitute those values in the profitability formula, then you get that the profit at point A is equal to 0. That is the determination that has been done here. That's the calculation or the enumeration that has been done here. By eyeballing this point, this extreme point, we can see that the coordinates are 0 and 0. And if you substitute that in the profitability formula, you determine the profit level at point A is equal to 0. The other point is at point B, the other extreme point. Again, you can determine this by eyeballing, and we will see how to show these coordinates. And at this point, we can see that the coordinates are 0 for x and 180 for y, right? And therefore, you can also determine the profitability at this level when you substitute 0 for x in the formula and 180 for y in the formula. You end up with a profit level of 54,000. Now, it is not we can also do the same for point E, where we can determine the coordinates by eyeballing, right? And when you eyeball, you can see that at that point, at that extreme point, x is 174 when y is 0. So when you substitute this in the formula, you end up with a profitability level of 60,900 at that point. However, these 2 points, C and D, are a little bit different. They are away from the axis, they're in the quadrant of the graph, and eyeballing may not be very accurate. For example, at point C is the intersection of the pump and the tubing constraint. Yes, you can estimate by drawing a line there and saying this is about 120 something of the y-axis, and if you move across, it's about 70 something of the x-axis. Yes, but it is not very accurate. So eyeballing will not give us very accurate figures for the coordinates of C and D, particularly extreme points which are away from the axis, such as C and D. Now, to do this, we therefore make use of two functions: the matrix multiplier function and the matrix inverse function. The matrix multiplier function is called the mmult function in in Excel, and it is here shown, and the M inverse function as well. We have to use them in conjunction. So in the practical slide, we'll show how to use these two functions to determine the coordinate points as shown there, in order to determine the profitability at point C, and at point D we also determine the coordinate points in order to determine the profitability. We'll then compare all the profitability and decide on the optimal point based on the maximum rule of profitability. We'll now move out of PowerPoint and demonstrate these aspects practically. Turning to the Microsoft Excel demonstration, here we show the presentation of the algebraic formulation into spreadsheet format, which we had explained from the previous slide. Right, so we have reserved a cell for the quantities of products to be made. We have reserved a cell for the calculation of profits. We have captured the coefficients of the profitability function. We have captured the coefficients of the constraints. We have reserved cells for the calculation of left-hand side values. We have reserved cells for available capacity. Now, in the previous slide, we have also demonstrated how to calculate the coordinates, where we indicated when x for the first pump constraint, when x is 0, y is 200, while when y is 200, x is 0. Sorry, this was not transferred. All right, so these are the coordinates that we determined from the previous slide. So the first step in solving a linear programming problem is to draw the constraint of graphs, right? We want to show the lines of the constraints as had been shown in the previous slide. And to do that, what you need to do is, first of all, starting with the first constraint, highlight the cell range where all the coordinates are found, just as I have done. Then go to Insert, look for where the chart option is, all right? And we have Insert, Charts is right here. Click on this small downward pointing arrow and then select this option, Scatter with straight lines and markers. You need to pick the scatter with straight lines and markers because you are drawing a straight line graph. Remember, it's about linear programming, therefore the relationship is linear in nature and is represented as a straight line. So if you click on OK, then that first constraint graph will be represented as shown. And you can make changes to the chart as you so wish. For instance, if you want to change the chart title, you can make changes there by just deleting what comes there by default. Let's change that to Blue Ridge Hot Tabs as the name of our company. So that is really, just to make it communicate that this chart will be for this particular company. That is our line. Now, after drawing the first constraint by selecting the range of coordinates from there, you need to confirm that the way Microsoft Excel has picked that data is the correct format. Because we know, based on our formulation, that we want to call the Aquaspar products as X, while the Hydrolaxes as Y. So the data series must be correctly captured. And to do that, first of all, just click anywhere on the graph. And then to determine if the data series is correct, let me just move this up so that you can see the graph in its entirety. Click on the chart anywhere and then right click and then click on select data. When you click on select data, this window will come up and then you can make a number of changes. But what we are interested in is to determine whether this line, the data series has been captured correctly. And therefore you need to go there under series, click, and then click on edit. Under the data series, once that comes up you can name that line, right? And we know that line is referring to the pump constraint. There it is. And then under the series X values, you want to capture the values of the X values. That's what it simply means, that when it's talking about the series X values, you need to capture the X values going down. So you need to click at that point and then actually select that range, the X series values, click on enter. Go to the series Y values, do the same. Select the series Y values are 200 and 0, which is that. Click on enter. Once you have picked those series values, click on OK. All right, so what you have simply done is to ensure that the line being represented is accurate in this graph. Okay. While you are still in this pop-up window, you can add the labor constraint and the tubing constraint. Okay. So while you're still here, simply click on add. This will come up. We want to add the labor constraint. So just give it a series name. Let's call it labor. And then under series X values, we do the same as what we did with the previous constraint. Click on that point and then pick the series X values, 0.74, enter. And then now we want to pick the series Y values, but first let us delete what is here. Click on that point, select the series Y values, click on enter. You have now added the labor constraint. Click on OK. Once you click on OK, then the labor constraint line will be added automatically. And you can see Excel is giving them different colors. So these lines are already bounding the feasibility region, right? Feasibility region. Let's add the third constraint. Click on add. We now want to add the tubing constraint. Let's give it that name, tubing. Add the series X values as we had done previously. Select the series X values, enter. Delete what is there first, and then add the series Y values, and then enter. Immediately, it then adds the tubing constraint, further constraining the feasibility regions, pushed it down now, right? And if you click on OK, we now have those three constraints added. And if you click on OK, you have your constraints graph showing, the three main constraints. Of course, you know that the x-axis and the y-axis delimit the non-negativity constraints. Now, in the next demonstration, we are going to show how to delimit, or how to identify and show the feasibility region, and then determine the optimal solution using extreme or corner points, as is normally done in the graphical approach. Having drawn the constraint lines, what we now want to do is to establish the feasibility region and then determine the coordinates of the extreme points in order to calculate profitability at each of those points. We have already explained this, so I'm just showing this so that you know what you want to achieve. I've already explained how to determine the extreme points of those points that are lying on the x and the y axis, that you can do that by eyeballing those particular points. And then we will demonstrate in this session how to determine the coordinates of point C and D, given that they are lying away from the axis. all right, and we'll use the mmult and the minverse functions to be able to do that. All right, so what I will do now is just remove what I've done on this graph. To do it with you, I will first of all remove the shaded region so that I can demonstrate it. Right, and I will remove one of these points so that you can also demonstrate how to show that point. You can ignore this part for now. What you need to concentrate on is the graph. So what you want to do is to identify. We know that this is the feasible region. Remember that the kind of equations that we have are less than or equal to they are less than or equal to equations, right? For example, we know that 1x plus 1y should be less than or equal to 200. That is the pump constraint. The pump constraint is given by the blue line shown. All right. So to determine the feasibility region delimited by the pump constraint, let us pick any point. Let's pick a point such as that point there. That point there has the coordinates 150x and 150y. Right? And to determine if this point is in the feasibility region, substitute those values 150x and 150y into the constraint. 1x plus 1y should be less than or equal to 200. Now, if x is 150 plus 150, that is definitely more than 200. 150 plus 150 is 300. So at that point, the constant value is 300. It is out of the range of the 200 value. So we can therefore tell that any point on the right side of the constraint line is outside the feasibility region. What about if you take a point such as that point? That point has the coordinates 50 and for x and 100 for y. If you substitute it in the constraint formula for the pump constraint, we have 50 for x, so 50 plus 100 is less than 200, right? So that point is at 150, which is definitely below 200. So it identifies the feasibility region as this point. You can do the same for the other constraints, and you will determine that the feasibility region is bounded by this line, that's the tubing line. Then at that point, it is further constrained by the pump constraint, the blue line. Then at point D, it is forced down further by the labor constraint, the orange line. And then the other boundary is the x-axis and the y-axis. So we need to shade that region, and you can shade that region by making use of the shapes that you find in Excel. For example, if you go to Insert, I believe, let's go to Insert, Shapes, and then if you look at this region, this feasibility region, it almost looks like a right triangle, and therefore we can make use of a right triangle to delineate or to select that section. Go to Shapes, and we have a right triangle right there. Then once you've picked the right triangle, come to your the point where you want to start shading this region. Click on it, hold down the mouse key, drag it down along the line. Try as much as possible to be along the line. Don't go beyond. Sometimes you could, but you can correct it. And that is the first step. So we have captured that first step of covering as much as possible the shaded region. But there's still a section here that we need to cover. Therefore we can improve this by editing that section. once it is highlighted and you go to edit shape and then select edit points, it will then highlight the specific points of this shape you put here. If you go to the edge, you can click and hold down and move it towards as much as possible to the line where you want it to be, right, to cover the shaded region. And this is just for demonstration purposes. So we have now shaded our feasibility region, right? You can label it. Again, you can still make use of the shapes that are available within Microsoft Excel. Let me use the rectangle with rounded corners. Click on it, bring it there, right click, edit text, and just type in feasibility region. Okay, and you can make it look as good as you want it to look. And so we have shaded it. The next point is we indicated that we need to calculate profitability at each of the extreme points. Point A, point B is there showing 0, 180 coordinates. Point C is at that point, right? We've just put it above the point where the tubing constraint intersects the pump constraint, while point D is right there where the labor constraint intersects with the pump constraint. So these labels, again, you just use shapes. If you pick circle, click there, and then give them a label. For example, if I want to put a label there, go back to shapes, or just copy one of these that you have put there, and then if you paste, it will appear somewhere. Just move it wherever you want it to be. So we want to label that point B, and then put point B. So remember, we inserted these labels by using shapes, the same way we have shaded this region. So we have now labeled the points, right? And we have determined the coordinates for some points by eyeballing them. Point A, B, and E, we have determined their coordinates. Point A is 0, 0, and we have determined the profit there. Point B, we have determined the coordinates, and we have determined the profit there. Point E, we have done the same by eyeballing and determine the profitability. We need to determine the coordinates of point C and point D by using the two functions mmult and minverse functions. And for us to do that, we need to create a section in the spreadsheet where you want to calculate what are the x and the y values where these two constraints intersect, the tubing constraint and the pump constraint at C, and also x and y values at this point. If I move across the spreadsheet, I'm just going to move across spreadsheet. Let me stop it first, and then we will. Right, so we have now determined our feasibility region. We now want to determine the coordinates of C and D so that we calculate the profitability at those extreme points. And as I've indicated, set aside a section of the spreadsheet where you need to calculate the coordinates for X and Y for those 2 points that are away from the x-axis. And for you to do that, just set a section aside. Remember, what you need to use the mmult and the m-inverse functions is to use the coefficients of the constraints that are intersecting at those points. At point C, we have the pump constraint with the coefficients 1, 1, and the right-hand side value of 200. And for the tubing constraint, which has the coefficients 12 and 16 with capacity of 2,880. At point D, these are the two constraints that are intersecting with their coefficients and right-hand side values, both pump and labor. at point D. So what requires to be determined is what is the value of x and y? What are the coordinates for x and y at that point? And it is these values that you then use to calculate profitability. So first of all, let me delete what is showing there so that we do it all together. So when you start, okay, so we now have, there are no values here. We want to determine, we cannot eyeball. If you eyeball, you're not going to estimate correctly. So we want to use the M mult and the M inverse function. Now for you to do that, you need to select these two cell locations together first. You must use that procedure, otherwise you'll get it wrong. So select the two cell ranges where you want the values to be calculated, then put in your equal sign, then start by typing the M mult. Once it appears, you can click on it, and then the second part of the syntax is M inverse. Once it appears, click on it, and then it will automatically put in the first opening brackets, which allows you to select the first range of data. And the first range of data you need to select are the coefficient values for the two intersecting constraints. And the range of data you need for that first range is that section which is highlighted. Close the brackets, then put in a semicolon, and then put in the second range of values. The second range of values are the right-hand side values of the constraints. So select them, close the brackets, but do not enter first. After you've closed the brackets, you need to select Control Shift Enter at the same time for the operation to work. So press Control Shift and Enter at the same time, and you can see the values are automatically calculated, showing you that at point C, the coordinate for x is 80. At that point, x will be 80, and if you eyeball, it is somewhere there. And the coordinates for C is 120, right? 80 and 120. So to determine profit, you simply substitute for the values in the profitability function as we have shown here, which gives you a profitability level of 64,000. You can also calculate by inputting a formula there, all right? And we know that to determine profit, you have to multiply the value of X with $350 and the value of Y with $300. We now have a value of X as 80 for point C and the value of Y as 120, for the tubing constraint. So to get the profit, if you input a formula, put in your equal sign at that cell, what you want to do is to multiply that value, 350, times that value, 80, plus 300 times that value, right? So and we are adhering to design aspects. We are not putting in numeric constants. We have basically referred to the cell ranges B5 and C5, right? And because this cell range will remain fixed as we look for the solution, we can make the cell locations absolute by putting dollar signs in front of the B and in front of the 5, as well in front of the C and in front of the 5. And once you enter, it will calculate the profitability at point C as $64,000. Right? So definitely it is higher than the profitability at point B. It is higher than the profitability at point A. It is still higher than the profitability at point E. But I'm going through the same procedure again. Highlight the two cell ranges that you require to determine their values. You want to determine the value of X there and the value of Y there. Put in your equal sign. Then the mul function is coming up. You can click on it. The second part is the M inverse function. Click on it. Then after the open brackets, the coefficient values required for pump and labor are there. Select them. Close the brackets. Put in a semicolon. And then the second range required, the right hand side values, select them. Close the brackets. Before you hit enter, press Ctrl Shift enter at the same time, and then the values will be calculated. And here it is shown that the X value at point D is 122, while the Y value at point D is 78, right? And you can determine profitability the same way that you did, in determining the profitability at point C. If we copy the formula there from point C to point D, it shows us now that the profitability at point D is $66,100. All right. Now, if you look at the M inverse function, it gives you the syntax. The outer curly brackets are actually put by Microsoft Excel. So what you put in are from the equal sign all the way up to that close brackets just after the S10. The outer ones are actually put automatically by Excel, so you don't put those outer ones in your formulation. So by using Microsoft Excel, we have been able to formulate a linear programming problem, a product mix linear programming problem, which we have solved graphically by drawing the constraint lines, determining the feasibility region, determining the profitability at extreme points. And we are now able to tell that the optimal point is the point where the company produces 122 units of Aquaspa and 78 units of Hydrolax. So point D, in this particular problem, our interest was to determine what is the optimality point. Point D is therefore the point of optimality, which identifies the maximum profit. Out of the 5 extreme points, the maximum profit is $66,100. And this is the approach to employ when you want to solve an LP problem graphically. Thank you.